Okay, so I mentioned electrolysis in a couple of other videos. Electrolysis is essentially the opposite of a galvanic or a voltaic cell. It's running one backwards. That essentially is not a spontaneous process. You have to actually apply a voltage to it. Essentially, it is the backward reaction for any spontaneous reaction. So it's causing a non-spontaneous reaction to happen. That's how we recharge batteries. Okay, so we can make non-spontaneous reactions occur. We have to just use electrical energy to reverse the flow of electrons and do the non-spontaneous reaction. Okay, so galvanic or voltaic are the spontaneous ones that would have like a voltmeter that measures the voltage. An electrolytic cell is one that we run backwards and you have to supply a voltage for. Okay, so opposite of voltaic or galvanic, a non-spontaneous reaction driven by applied electricity. So there's a couple different types, two different types specifically of electrolysis. I am going to talk about aqueous really quick just because it is much easier to do in reality than molten. That's the second one down here. Okay, so there are two types of electrolysis, and molten will get you your results that you want very well, but it is very difficult to do because the term molten means you have to have like molten salt or essentially whatever you're looking for. So I'm going to talk about aqueous first because, like I said, that is much easier to do. Now, the process for figuring out what's going to happen, though, is a little bit more difficult. So essentially in an aqueous electrolysis solution, so exactly what was above here, this would be an aqueous electrolysis solution. It's in water. Okay? Ions are present in the solution of water and only requires the energy necessary for electrolysis. Okay, so if I have salt, for example, and I would like to electrolyze it, okay? So the first thing I want you to do, whatever I tell you I am trying to electrolyze, I need to look at those ions, okay? Because that's what I have. I have Na plus and I have Cl minus. So whenever you're trying to electrolyze something and we're trying to actually turn it into the pure substance, the metal or the gas or whatever it is that it is. Okay, so I would be wanting to turn Na plus into Na solid, and I would be wanting to turn Cl minus into Cl2 gas. So back to its pure form. So what I want you to do is actually look up the sodium and the chloride equations on your reduction potential sheet. Okay, so when I'm looking at these ions, one of them I need to oxidize, one of them I need to reduce. So if it was sodium, okay, this is the sodium reaction from our sheet. Sodium plus 1 electron makes sodium solid. It's negative 2.71 volts. And chloride is 2 chloride minuses make 2 chlorine gas plus 2 electrons, and that's negative 1.36 volts. Okay, so I just pulled those from our reduction potential sheet. Now, which one am I trying to reduce and which one am I trying to oxidize? Okay, well, I'm trying to reduce sodium because I have the ion Na plus, and I'm trying to make it to Na no charge. So that would be going down in charge. And the chloride, I am trying to oxidize. I've got Cl minus, and I'm trying to make it Cl2 with no charge. So that would be raising the charge. So I'm trying to reduce sodium and I'm trying to oxidize chlorine. So I would say, well, at my cathode, I want this to happen. And at my anode, I want this to happen. Okay. Now, the problem with it being an aqueous solution is that it is also possible to reduce or oxidize the water. So you have to take into consideration that that is also a possibility, and only one of them, whichever one is more favored, is going to occur. So the fact that we're in an aqueous solution means, well, I might do this, that's what I want to do, but I could also do this. I could do the 2 waters plus electrons makes H2 plus 2 OH minus. And that is negative 0.83 volts if you pull that off of our reduction potential sheet. Okay, so this is the reduction of water. I could also oxidize water. So at the anode, if I have water, I could do this. I could turn water into O2 plus 4H plus 4 electrons. Now, how do you know to specifically pull these two equations? Well, I do put those two equations specifically on your equation sheet. Let me show you. So see here at the bottom of your equation sheet, I've got the reduction of water is negative 1.23 volts, and the oxidation of water is negative 0.83 volts. So either of these reactions could also happen. So when I go back to the notes, essentially what I'm doing is at the cathode where reduction happens, it can either be what I want or water being reduced. So what you have to do is look at the values, and whichever one is more positive is going to occur. That's the one that is easier, right? The higher it is on the reduction potential sheet, the easier it is going to reduce. Okay, so it's negative 0.83 volts versus negative 2.71 volts. And while this is technically less negative, it is more positive, that means that this is actually what is going to happen at the cathode. So I wouldn't be doing what I wanted to. I wouldn't actually be reducing sodium. I would actually be reducing water if I was trying to do this in aqueous solution. Now, this does work for a lot of things. Essentially, anything that is higher than negative 0.83 volts will reduce in water. It's just that this one will not. Okay, we're going to check the same thing for the oxidation reaction. So I pulled the chloride ion off of that sheet. It's negative 1.36. And this is the water one, which is negative 1.23. Okay. So I do want you to first notice that, right, we're looking at oxidation. So I did flip the chloride reaction because the whole sheet, let me go back to that sheet, is reduction potentials, right? So I looked for chlorine. Chlorine is, oh, right, chlorine's up here, right here. And I'm trying to oxidize it. I'm actually trying to get the chloride ion to turn into the gas. So I'm reversing it. So I'm reversing the sign as well. Okay, I'm trying to do the opposite. So it's negative 1.36. So if I go back, this one is negative 1.36. Water's is negative 1.23. And since this is a little bit more positive, water is actually what is going to oxidize at that unit. Okay, so you check your reduction equations, you check your oxidation equations. Whichever one is more positive is the one that will occur. Now you do have to flip this one. You have to make it written the way that you want it to actually occur, which means you're going to have to flip the sign. But then whichever one is higher or more positive is going to be the one that actually reduces or oxidizes. So if we actually tried to do aqueous electrolysis with NaCl, we wouldn't be able to get the results that we want to because the water would actually reduce or oxidize instead. Okay, like I said, though, there are a lot of things you can do this with. Essentially, anything that is higher than negative 0.23 volts will oxidize, and anything that's higher than negative 0.83 volts will reduce. Okay, so you just want to compare those values and decide, is that going to happen or is it not going to happen? Okay, so if it's not going to happen, sodium chloride, I can't turn it into solid sodium and chloride gas using an aqueous electrolysis. The other option is molten electrolysis. Now, molten electrolysis is always going to get you what you want because there's no water involved that could reduce or oxidize. So molten electrolysis is what I actually do is I use pure molten sodium chloride, no water, to do the electrolysis in, because the only option then is for the chloride ions to turn into chlorine gas and the sodium ions to turn into sodium, well, in this case, liquid, which as it cools will be solid. Now, molten salt is really, really, really hot. So this is very difficult to do in reality, but it would give you the exact results that you want. Always, molten electrolysis will always work. Okay. So essentially what you have to do is you're going to predict the products using the electrode potentials from the sheet, just like I showed you. Make sure if it's aqueous that you compare it to these other two possible reactions for water. Be like, okay, which one is higher? Which one is going to actually react? Okay. So I've got example number 11 says an aqueous solution of nickel chloride is electrolyzed. Okay, what are the products of the cathode and anode? What would the results be any different for molten salt electrolysis? So essentially, molten salt we always know is going to get us the products that we want. However, aqueous maybe not. So we have to check our values. So what I did is I first wrote down the ions. So I've got nickel 2 plus and I've got chloride minus. Nickel 2 plus I would then want to turn into solid. So we're trying to get it back to its solid state. Or you can look at the sheet. And chloride, I'm trying to get to chlorine gas. So if you look at your, not the equation sheet, this one, I've got chloride. Okay, we're trying to do the reverse reaction. So I wrote negative 1.36 when I pull that one. And nickel is down here. Okay, I'm trying to do this forward reaction. So I got negative 0.23 volts. Okay, so I should pull those two numbers and I want to compare them with the water numbers. Okay, so at the cathode, which is reduction, water's reaction is this, which is negative 0.83. That is on my equation sheet right here. Reduction of water. Oh, wait, sorry. Am I doing the anode? I just realized that this is incorrect, so I'm going to have to go in and fix it. But essentially, I have the wrong water equations, right? If you actually look at the ones above, the cathode should be negative 0.83. Wait, it is. And the anode is negative 1.23. I apologize. This is right. It's the equation sheet that's wrong. So I need to relabel the equation sheet. Sorry, I have them on here. That one should be oxidation and that one should be reduction. So I'm going to fix those. But let's go back anyway to this. So I'm pulling from right here. These are correct. Okay. Cathode, the reduction, and anode, the oxidation, right? Losing electrons to oxidation. It's negative 1.23. So I pulled those down here. So the cathode, I am checking this equation. So cathode is reduction. So I check this equation, which is negative 0.83, versus the nickel one that I'm trying to do. I am trying to oxidize nickel. Sorry, I am trying to reduce nickel. Goodness gracious, which is negative 0.23 volts, which I pulled from the table. And then at the anode, I am trying to either do the water one, which I pulled from right here, negative 1.23. Or I'm trying to get chloride to turn into chlorine gas. So 2Cl minus makes 2 electrons plus Cl2. So I'm going to go back and show you where I got this negative 1.36, right? Chlorine. Okay, remember I'm trying to do the opposite reaction, so that would be negative 1.36. Okay, so then I compare these values. I'm like, oh, this is actually more positive or more spontaneous than water. So I could do the nickel part. However, chloride is not going to work for the same reasons that we did speaking above. So the question, or the answer to the question is, then what are the products at the cathode and anode? So if I'm doing it as aqueous, then the products at the cathode would be nickel solid, and the products at the anode would be oxygen gas and 4H plus, essentially. You don't have to list the electrons. Okay, so these are the reactions that would actually happen. Said, would the results be any different for molten salt electrolysis? Well, they would, because in molten salts, I get what I want. So I would be able to make nickel solid and chloride gas or chlorine gas. Okay, so they would be different. Okay, so why don't you try example number 12? Make sure you pull from right here, and I'm going to fix the equation sheet so that that doesn't happen. So go ahead and pause. Okay, example number 12, I did the same thing. I pulled my cathode reaction, my reduction reaction for water down, and my oxidation reaction for water down. Okay, this one is negative 0.83, this is negative 1.23. Those are always going to be the same. Okay, now I've got magnesium iodide. So if I look at my sheet, magnesium is down here. Magnesium is right here. Negative 2.37. Now this is what I'm trying to do. I have magnesium ions plus 2, so I'm trying to turn them into magnesium solid. So negative 2.37 is what I should pull for magnesium. And for iodine, iodine is here. I'm trying to turn iodine minus into I2. So that would be the reverse of this reaction. So I need to pull the number negative 0.54. So if I look over here, I put negative 0.54 because I'm trying to do that reverse reaction. And this one is negative 2.37. So if I look at my numbers, well, this one is higher for the cathode and this one is higher for the anode. So I could do the iodine part, but not the magnesium part. So the answer is, what are the products? Well, I would make hydrogen gas and 2 hydroxides. I would also make iodine solid. Okay? So the answer to the second part is yes, we could only reduce magnesium if it was in. Okay, so applications of electrolysis, where do we use these? Well, we can actually do electroplating. Whenever you want to plate something with a metal, you can stick it in the solution and we can get it to plate, like a copper plated key, for example. And we can also purify metals this way because we can get them to deposit, right? When we get things to turn into solids that we want, then we can collect that solid essentially. So we can do that to purify metals as well.